Hello guys, what is shishodoshi? It's an agricultural device in Japan. It was originally used to startle any herbivores, such as deer or birds, which may be grazing on the plants. So its function is similar to scarecrow. Both of them are used to frighten away animals. In the picture, we will find that the device is placed in a irrigation ditch. Let's see the diagram of operation. It consists of a segmented tube, usually of bamboo, pivoted to one side of its balance point at rest. Its heavier end is down and resting against a rock. A trickle of water into the upper end of the tube accumulates and eventually moves to the tube center of gravity past the pivot, causing the tube to rotate and dump out the water. The heavier end then falls back against the rock, making a sharp sound, and the cycle repeats. Nowadays, people found that the sound of shishodoshi is relaxing and include a few of them. It boggles the mind how something so simple could at the same time be so ingenious and calming. With nothing in the air but the rhythmic and rather hypnotic sounds of the shishodoshi in the background, you truly get a serene and meditative moment. Water from a bamboo spout fills one end of the bamboo tipping piece, which triggers a seesawing motion, and the water is then emptied from the tipping arm into the bowl or pond, whilst the tipping arm is propelled back into position with an audible sounding rock. In the tranquility of the Japanese garden, the rhythmic sounding sound is intended to cause visitors to reflect on the passage of time. Therefore, people move this device into their garden as a part of the decoration. Moreover, shishodoshi appears in anime, the bamboo filling with water and then making that distinct sounding sound is often used as transition card. We initially discussed the topic about time, which is a very broad concept. We choose 4 regions from the teacher's PPT, which are gravity, electricity, chemical reaction, and others. After polling, we choose gravity, and we finally came out with water clock as our topic. After several proposals, Zhang Chenjia came out with an interesting idea. It was shishodoshi, which is not a clock but can act as a timer, since the flow of water and capacity of a tube can be controlled. We can decide when the tube rotates, so it will become a timer. If we can cascade shishodoshi with different capacities, we can build a clock where the top tube counts 30 seconds and the bottom tube counts 1 minute. In theory, we will include our experiment data as in the next part explained by Tianongsen. During the real experiment, we only can yield 6 seconds for the top tube and 60 seconds for lower tube. The next speaker will elaborate.
So hello guys, I'm going to explain our calculations for this particular project. So here's the basic formulas that we're going to use for this project, which are a torque formula and flow rate formula. It's pretty basics actually, pretty basic physics, and I bet most of you already know these from high school or even middle school, so I don't need to elaborate more in this particular section, and I assume you all already know the formulas. So I use those, as I mentioned, It's pretty basic, but you know, the formula is really easy to use, and it can relate volume, mass, weight, time, and flow rate. So our aim is actually to make a water clock. In order to make a water clock, we have to need those variables. We need volume, mass, weight, time, and flow rate. So yeah, it's really crucial. So therefore, we utilize those formulas. Here's the data from the experiment. Short bamboo. We actually have two levels of bamboo tubes. The higher one is actually 42 centimeters in length. The longer one, the bottom one, is actually 57 centimeters in length. And here's the pivot point for both bamboo tubes. Here's the mass. So actually, each bamboo tubes we actually combine them together. One is for containing water, the other one is for the pivot point. So you can see the data. I don't have to really mention it. Yeah, we also have the extra mass for the lower bamboo, for the longer bamboo, because the lower bamboo doesn't really weigh that much. And here's the height of the pivot of each pivot, which is really crucial for us to verify the mass. Here's the documentation. Here's what it looks like. First level and second level. So I'm gonna really quickly discuss our calculations. So the first bamboo needs approximately 6 seconds to turn. So we know the flow rate from I believe the pump. We actually use a pump, so we just multiply it by the time you need to turn and the flow rate. So therefore we get the mass. And remember, 1 kilogram of water is equal to one liter of water because of the density of water. So you can ignore the second these calculations and just go directly here. The second volume, the second bamboo needs 5 to 6 turns to actually fill it up. So here's our calculations. Here's the mass. So the first volume is 18. The second volume is 99 grams. So yeah. So we must verify it. How to verify it? Simple math. We use torque again. We use torque. How? By finding the angles of each of these, and we compare it. Torque is actually a length multiplied by weight, which is length times mass times acceleration of the gravitational acceleration of Earth. It's really simple. We yield each angles, and we eventually we already proved that the torque in this part is actually larger than this part. So therefore it turns this as well. So therefore we already prove the weight. We already justify the weight of the water. Here's the simple calculation. So in the first bamboo, if we want to have 10 seconds, the flow rate must be 1.8. If we want second bamboo, if we want 60 seconds, we have to have 1.65 milliliter per second. But it's really impossible to actually have different flow rate. Therefore, we must change the volume instead if we want to have the same flow rate. Either we change the first tube into 16.5 milliliter, or the second tube into 108 milliliter. So that's it, guys. Thank you.
Hello everybody, I'm Chuck, and I'm going to introduce the Python simulation of the Shishi Odoshi clock. So first of all, I'm going to introduce the Python code and explain the parameters that are needed and the roles in this code. So first of all, the water flow F. It is the most important part of it because it can create a sustainable and continuous water flow which is related to the time, and we need it to have a clock. And The other parameters that are very important is the weight of the bamboo, the center mass of it, and the time that we restricted to make it incline. So first of all, the weight of the bamboo can be scaled, or it can be approximately counted by using the thickness, the density, the area, and the length of the bamboo. So we can get the approximate weight of the bamboos. And the center of mass can let us know about the torque that is caused by the bamboo itself. And we also need the pivot spot of it and the beginning spot where the water can start to accumulate. So we just set it as same as the previous spot, which is called B1 and B2. And the time control, the time that we wish that the bamboo 1 and bamboo 2 will incline. And the under is the formulas that is needed for the resolution, for the results. And so we first key in all the parameters. These parameters are the same as our experiments, which is showed in the video. The water flow is 3 milliliters per second. Thickness is about 0.3. The mass center is measured by hand and the other parameters too. So we restricted the bamboo 1 to incline in 10 seconds and the bamboo 2 for 60 seconds. And the results tell us that it is nearly 33 seconds for bamboo 1 to incline and 45 seconds for bamboo 2 to incline, and which is not as restricted wishes. So we need to add to 12 grams for bamboo 1 and 585 grams for bamboo 2. Or we can change the length of the bamboos, like make bamboo 1 41 centimeters and bamboo 2 53 centimeters. Or we can also change the pivot location, which will be 20 for bamboo 1 and 25 for bamboo 2. So there are still some deviations that we need to overcome to make the simulations as correct as the experiments. So first of all, the frictions are not counted in my simulation. So the friction caused by the pivot and the bamboo are not counted in, and it will increase the time of the bamboo to incline. And the water can drip in the bamboo properly, which means that the time for the bamboo incline will become longer, and the momentum caused by the water drop will cause the incline time become quicker. These are the deviations that are not counted in the simulations.
Hello, here is Shu Guozhi. I'm going to tell you about the implementation part of Shishodoshi. This is our original design in our midterm project. Originally, we think we will use 3 bamboo tubes here, and each one will count maybe 10 seconds, 20 seconds, and 40 seconds. And there will be a motor under the water. It will pump the water up to the height here and drop the water into the first tube. The water will accumulate from the bottom here. And after 10 seconds, the tube here will rotate and drop water into the second tube. And after 2 times of this process, which means 20 seconds, the second tube will rotate and drop water into the last tube. And after 2 times of this process, which is 40 seconds, the last tube will rotate and drop water back into the pool. However, when we implemented our design, we met some problems. First, if we only use one section of bamboo tube, it doesn't work because the center of mass will never move cross pivot. In this photo, we assume that the red line here is where the pivot is, and in the beginning, the left part is a little heavier than the right part. So when the water drops into this tube, water will accumulate from the bottom here. And since in the beginning we had already told that the left part is heavier than the right part and water accumulates from here, so during the whole process, the left part will always heavier than the right part, and the tube will never rotate. The second problem is that the motor we use can pump water up to the height we expected. So this is our solution. For first problem, we combine 2 sections of bamboo tube to make shishiodoshi. Similarly, we assume that the chopstick here is where the pivot is, and in the beginning, the left part is a little heavier than the right part. Since this time we use 2 sections of bamboo tube, so when the water drops into the tube, the water will accumulate from here, and so it will cause the mass of center move from somewhere here, cross the pivot, and make the tube rotate. The solution to second problem is that we reduce 3 tubes to 2 tubes, so the motor can pump the water to the height we need it. This is our new design. We set the above one 10 seconds and the other one 60 seconds. And to set it to 60 seconds, we add a loading weight here on the left side. So the torque in the left side will be bigger, and so we need to drop more water into it to form a bigger torque in the right side, so it will make the tube rotate. So this is our implementation. As you can see, each rotation process takes almost 10 seconds for above one. And after 60 seconds, this one will rotate and drop the water back into the pool. And since during the process, we will lose some of water. Not all of water will drop into the second tube. So this will make our implementation have an error between. So there will be an error between our implementation and our calculation. And thank you for listening.